Hello and welcome! Get ready because in today's explainer, we're literally going to put on our mechanical X-ray glasses. We're going to strip away the plastic and metal casings of the objects we touch every single day and look right at their beating hearts. To make these concepts really pop and easier to grasp, we'll be visualizing these incredible inner workings in a playful, tactile clay style. It really helps you physically feel exactly how they move.
Think about this for a second. When you turn on a standard motor, the drive shaft spins in continuous circles, right? But out on your windshield, the wiper blade swings left, then right, then left again. So how does a spinning motor make a windshield wiper swipe back and forth? Honestly, it kind of feels like a magic trick, transforming one type of movement into a completely different one. But as we'll see, it's just brilliant mechanical design.
Okay, let's dive into this. Here is our blueprint for the explainer today. 1. The magic of everyday machines. 2. Kinematics, the language of motion. 3. Gears, speed versus torque. 4. Linkages, connecting the dots. 5. Mastering time, intermittent motion. And finally, 6. Your world in motion.
Starting off with Section 1, the magic of everyday machines. To really understand the complex devices all around us, we first need to get our definitions straight.
We throw these words around a lot, but engineers use them very specifically. Notice the subtle but absolutely vital distinction here. A mechanism is a system designed to transmit motion. Think of the low-force sliding parts inside a folding chair or the linkages in an umbrella. But a machine? Well, a machine is designed to transmit motion and energy. It involves significant forces, like a heavy-duty piston engine. And get this, a simple hinged door doesn't even qualify as a mechanism. Why? Because a mechanism actually requires multiple moving parts working together.
Moving right along to Section 2, kinematics, the language of motion. Now that we know what we're looking at, we need the scientific vocabulary engineers use to describe how these things actually move.
And that brings us to kinematics. So what is it? Kinematics is purely the study of motion. It looks at position, velocity, and acceleration. It's basically all about geometry in motion, entirely separate from the actual physical forces pushing on the bodies, which, by the way, is a different field called kinetics. Good kinematic design allows us to map out exactly how a system will move before we ever have to worry about the heavy forces involved.
A massive part of kinematics is understanding degrees of freedom. This is simply the number of independent inputs required to completely control a system's position. Think about a really complex car suspension absorbing a bump, the bucket of a heavy backhoe digging into the dirt, or even the lock and grip of vice grips. Engineers have to calculate exactly how many inputs, like hydraulic cylinders or manual levers, are needed to control every possible direction those parts can move. All right, Section 3, gears, speed versus torque. Let's talk about one of the most famous and ancient mechanical building blocks. The history of the gear is incredibly old. We can actually trace it back to ancient Greece in the writings of Archimedes over 2,000 years ago. Gears are essentially just wheels with carefully carved projections, or teeth. When they mesh together, they transfer rotational motion and power from one shaft to another. And because those teeth physically interlock, they allow force to be completely transferred without any slippage at all. That is a massive advantage over something like a smooth pulley system.
Now, what's really interesting here is the concept of mechanical advantage, which we're representing here with a 4-to-1 gear ratio. Imagine a small gear with 10 teeth driving a larger gear with 40 teeth. For every 4 times the small one spins, the large one turns just once. You are literally trading 4 fast, low-power rotations for 1 slow, highly torqued, powerful turn. This table perfectly captures the universal give and take of mechanics. It's the golden rule of gears. If a small gear drives a large one, your output speed drops, but your torque, your twisting power, goes way up. Conversely, if a large gear drives a small one, you sacrifice that torque to get a much faster output speed. You basically just have to choose what your machine needs most.
Section 4, linkages, connecting the dots. Rotating gears are fantastic for sure, but what if we need to reach out, push, pull, or change directions entirely? That's where we shift our focus from gears to linkages.
Check this out. This is the fundamental 4-bar chain mechanism. Notice how you have rigid, unbending links connected by pivoting joints. By holding one link fixed to the ground and moving another, this simple chain translates a basic input into incredibly complex, sweeping paths. In fact, this is the exact principle driving that back-and-forth windshield wiper we talked about earlier. Now, let's look at a very specific linkage, the toggle mechanism.
Think about the sheer crushing force of heavy-duty tin snips cutting through sheet metal. As you squeeze the handles together, the rigid links inside approach a straight, collinear line. In that tiny fraction of a second, the mechanical advantage spikes toward infinity, delivering an enormous, powerful bite over a very short distance. It is such a simple setup, but devastatingly effective.
Moving on to Section 5, Mastering Time, Intermittent Motion. Up until now, the motion we've looked at has been mostly continuous, but what if we need to master time? How do we make something stop, hold its position, and then start again precisely, while the motor driving it never stops spinning?
And this brilliantly illustrates two completely different ways to solve that exact problem. On the left, we have the ratchet and pawl, and on the right, the Geneva mechanism. Both of these take a continuous input and ingeniously slice it up into controlled, intermittent steps.
Let's look a little closer at the ratchet and pawl. That toothed wheel is the ratchet, and the little lever dropping down is the pawl. It allows motion in only one direction. As the wheel turns, the pawl slides up the curved back of the tooth and drops into the gap, physically locking it from spinning backward. This is exactly what allows a bicycle freewheel to coast smoothly, or what guarantees a heavy lifting jack won't suddenly drop its load. The Geneva mechanism, on the other hand, takes a totally different approach. A continuously driving wheel carries a small pin. As it spins, that pin slides into a slot on a secondary, cross-shaped wheel, turning it exactly one step before sliding out and locking it perfectly in place. This incredibly precise start and stop stepping motion was famously used in traditional film cameras to advance the film reel exactly one frame at a time. It held it perfectly still just long enough to capture the light. If the film didn't stop moving for that fraction of a second, every movie you've ever watched would just be a blurry smear. Wild, right?
Bringing it all together in Section 6, Your World in Motion. From Archimedes' ancient toothed wheels to the precision linkages inside a modern engine, it is amazing to see how these fundamental rules of kinematics govern everything around us.
But before we wrap up, we have to remember the absolute overarching rule of the physical universe holding all of this together. You can use mechanisms to cleverly trade speed for torque. You can change rotation into a straight line, but you can never ever cheat the total energy. The input power will always equal the output power, minus whatever you lose to the friction of the moving parts.
So the next time you use a pair of vice grips, or ride a bicycle, or just watch your windshield wipers slice through the rain, I really hope you use your new mechanical X-ray vision. Look past the casing. Think about the gears, the linkages, the degrees of freedom making it all happen. I'll leave you with this. Look around your kitchen or your garage right now. What hidden mechanisms are driving your world today?